so you have about 2 weeks ahead of time. Right now, I've got this lecture set. But I'll try and get about 2 weeks ahead. But they're pretty stable. I've been doing this for 5 years, so they're not going to change too much. But you'll note, if you look down here at the bottom, there's a date someplace, and if it says 2016, I haven't updated it yet. Okay, so let's, a couple other things. This is the rest of the schedule. There are going to be two tests, a midterm and a final test. And so these are the only tests in the semester. There's not going to be a final exam per se, but on the final exam day is going to be a poster day. So you'll do a big project as part of the class, and the final part of the project is presenting a poster. And so a time when I know you all are available is during the final exam at the end of the semester. In the past, I've made it in like the gap day between the end of the semester and the start of finals. And that has some advantages. I might be traveling that day, so I've put it here for now. If I'm not, I'll try and give you enough leeway ahead of time. But these 3 days, even if you're a remote student, is it streaming online? No?
Yeah.
Oh, great. So welcome to all the remote students if you didn't make it here. The 3 days you need to make it to class, definitely need to make it to class for the midterm, the end term, and the poster. Okay? Okay, so a little bit more about the project. If you click, if you see in this column here, this is the homework. These are the deadlines for the homeworks. I put them in the day that they're due, and when the homeworks are available, I'll post them on Canvas, and these links will become active. But then this column here is for the project. And so if you click on one of these links, then you get this PDF about the project. Okay? So the project will be 45% of your grade. So it's a pretty big part of the grade of the class. And so, unlike most classes you probably had, there's a project due at the end of some point at the end of class. And some of you probably wait until the last week to start working on it. I think this is not how it's supposed to work. And so I will have several intermediate deadlines, so you can't just do it in the last week of class. And I think this makes the projects a lot better. You learn a lot more. It has one challenge though, right? I'm asking you to do a project before you've learned some of the material that the project is about. But don't fear. There's not too much due early on, but it's stuff that takes a surprising amount of time. So let's see. So at the end of January, you'll have to do a project proposal. So this is just a short topic. What are you going to do it on? Form your groups. Okay. Then towards the end of February, about 3 weeks later, you have to do a small report on the data you've collected. So this usually takes a large chunk of the time for projects, getting your data in order to work on it. If it's just a programming assignment, you may not need to worry about this, but for this class, you'll be analyzing data. I hope that's what you've come here to learn how to do. So you'll need to collect data and massage it and get it into the right format and think about it. And this is something you should be able to do before you've learned all the material in the class. Okay, so this will be due towards the end of this will be due towards the end of February. In the middle of March, this is right after the spring break. So if you're planning ahead, you don't need to work on it during your spring break, but my feedback has been people actually like to have a chance to work on it over spring break. So right after spring break, you have this this report due. That's an intermediate report. You're not supposed to have completed things by then, but you should have gotten some basic infrastructure work. Enough and the point of this is so that you can get feedback on how to complete the project well. So I want you all to do well on the project. And if you wait till the last minute, I can't tell you, oh, you should have done this differently. You want to get enough done so I can say, this is what you should do to complete it to get a good grade on the project. Okay? And so you should make enough progress for that. Almost in the past, almost all groups have easily made enough project. There have been a few groups in past semesters who have just done nothing yet and they've lost points. But for most people, if you do some stuff and you've made enough where I can give you feedback, then that satisfies this requirement. Right? And then the final report is due April 17th. This is still like a week or two before the end of the semester. Okay, so this is, there'll be maybe 1 or 2 lectures after the final report is due. The reason for this is because we're also doing these posters at the end, and I want you to make a poster after you finish the project, so you can talk about it. Right, so you make the project, and then you have to do a draft of a poster kind of a couple days later, and then it takes a while. We'll print all the posters for you, and we need to make sure we have sufficient time ahead of this. Okay, so I might see if I can change these deadlines a little bit. I already, I think, pushed them back a little bit from last year because the poster session is a little bit later. Okay, but this is the general schedule. You'll see it on the webpage. Let's see if we see more about the report here. So there'll be a lot of questions about how big should this project be. Let me just say a few words now. I'll say more as it gets closer to the deadline for you have to do the project proposal. There are kind of 3 ways of doing the project. One is to kind of take some technique from class, and there'll be some techniques that we'll discuss that will be beyond what I specifically ask you to do on the homework. Right? I want to give you a touch of things that the homeworks will talk about, most of the core things you really need to know, but I want to give you a touch of kind of cutting edge. So taking one of these cutting edge techniques, and this will take a little bit, it'll be less clear how to do it than just on the homework, and applying this to real data and seeing how it works. Another way is to try a bunch of different techniques on a data set and see how they compare against each other. Which one was the right one to do? And as we'll see throughout the semester, this is very not obvious. We'll talk about this bag of tools that we have, and it's the challenge in many of these cases is not just knowing how these tools work, but choosing which one to use. Right? And so figuring out that by trying them is a good thing to do. And that takes some work to do correctly. And then, the third, you can propose something brand new and try that out and see how it works. Take an existing technique and say, it'd be a little bit better if I did this or that instead, and evaluate how well that works. Right? So these are the sort of things that you can do. It's not a huge undertaking, and you'll work on it throughout the semester, so it shouldn't be too bad. The proposal, we'll talk more about this later in the semester, but I want you to kind of just give me enough so I can say, I think this will work or I think this won't work, and to propose your group. Now the tricky thing is that only 100 or 200 words, really short thing. The tricky thing is you won't have seen all the material in class yet, so you may want to preview, look at the notes that are posted online and say, I'd like to do a project on this topic we haven't covered yet. And that's great. You should probably plan on doing that by just zooming ahead and browsing around what's up there. And then you can learn about it later and in time to do the project. And maybe read a little bit ahead of time. Right? And then to help you, in addition to this, a lot of people, this is not a class where I tell you, here's a fixed project, so go and do it, right? Some instructors like that, a bit more organized. I think that's very different from how, you'll be using this in the future. It'll be too constrained. I think it's better you come up with your own topic. So the best topics are going to be from some interest that you have. Someone last year was someone who was very into was very into hang gliding, and so he tracked the thermals that you could hang glide on and looked at trajectories and tried to cluster these. Right? I would have no idea that this was a project you could work on, but he knew of this data set and it was awesome, right? The best projects are from something that you're passionate about. That could be from something you're working on if you're part of a lab, or it's just some hobby you have that generates data. If not, another way to get ideas is I've linked to a bunch of websites that have just a bunch of interesting data sets. Just go look at these and browse these. You might get some interesting ideas there. You can ask me, is this going to be good or easy to work with? Please do that before the project proposal. I've been doing this for a few years, so I can give some pretty good feedback. This will work, this won't work. This is a tricky data set to work with. This is an easy one to work with. Some people want a messy data set, some people don't. I can help give this feedback. So best time to talk to me before and after class or in office hours, or over email works as too, but a little bit more burden on me. Yeah?
Is there any requirement for the data to be unstructured?
So no, you can get some nice structured data. So one of the things is, I kind of have a sense of how much overall work the project takes. If you're starting from much less structured data that you have to do more manipulation and working with, that counts towards the content of the final project. If you start with much nicer, cleaner data, I'll expect you to do a little bit more work with it because you're starting a little bit ahead. And so, depending on what you want, you can get different experiences, and they're both great. I'm very flexible in this regard. Okay. So let's see. So and then in the data collection report, we'll talk about this more later. The tricky thing will not just be having collected the data by this. It doesn't need to be final. You can change it afterwards. But in kind of thinking about how you've converted it into a format that you want to work with, some abstract data type. And we'll talk more about this throughout the semester. It's not just a file format, but kind of the mathematical way that you're going to model the data is what I want you to think about by this point. Okay? And then the intermediate report, be 1 page per student, not too long. Okay? That's 150 pages for me to go through, so that's a lot already. And then the final reports, I might have to make this a little bit shorter, but I have at most 4 pages per student. These 600 pages. Okay. This class was like 80 people last year, so I may have to tweak things a little bit, but this is the plan. If I will, we'll do this. And it's a lot of ideas, details about what I'm looking for in here. And then there's a lot of details about the poster. We'll talk more about this later. Okay. And great. Just people always ask me for example posters. Here's kind of what an example poster looks like. I'll bring in some a couple weeks into class when you're thinking more about the projects from last year, some good ones. But they analyze some sort of some data from atmospheric science and weather stations, ran some clustering on it, compared them, and so forth. So this was a one-person project, but you guys will almost entirely be working groups of 2 or 3. This was, I think, from maybe 4 or 5 years ago. So this was an older one. Okay. So, all right. So that's roughly how the class will run. I'll talk a little bit more about interacting with Canvas later. What I'd like to spend the next chunk of class doing is talking about what we will be covering in class. So what is data mining? How does this differ from many of the other classes that we offer here? When I first started teaching this, there was the only other comparable class really was AI, then there's the machine learning class, and I was more worried about how do I do 5 or 6 other classes you might think in this same space, right? So this is more of an introductory data analysis class that sits next to machine learning. Right? Let me talk a little bit more about this, right? So what is data mining itself? This is a term that is used in society in various ways. It's a catch-all phrase. How will we be determining this? Is it finding structure in data, machine learning on large data? Is it just unsupervised learning? Is it large-scale computational statistics? You know, so these are all things that some people this might be how you define data mining. None of these are really precisely captures exactly what we'll do in this class. So let me go a little bit more. I mean, I think I really want it to be how to think about doing data analytics. Okay, so the core of the class will be, you know, thinking about you're getting some data from some source. It could be messy, it could be cleaned up. How do you think about processing this and then doing some analysis on this data? Okay, so this is going to be a class where we cover a lot of different topics, a lot of material, and it's not going to go as in depth as other classes that are going to be more advanced at this. So I'll mention some of these. So it's going to be more broad, how to think about doing this the right way. What are the fallacies that can come up? How do you avoid them? Those sorts of issues. Things that you may not have realized are really important. So like principles of converting from some raw and messy data to some abstract representation. Right? So how many people have taken have taken a class in algorithms? Right? Okay, great. So in algorithms class, you're usually given a very specific problem formulation and you're asked to solve it very, very efficiently. Right? The problem is given to you, you're told exactly how the data is going to be, and then you can run, you want to be able to describe an algorithm that solves a certain problem. Right? And so algorithms is a big part of data mining and this class. But it's not, we're going to do some design of algorithms, but there's a huge piece of data analysis that's missing from that. You're often given data as kind of, you're given a big, you're given just like a book full of characters, right? That's text, right? You want to somehow do some analysis on that text. In order to deal with that, you don't just want to deal with it at the character level. You want to convert it into something else, into some nice format where we can then apply algorithms, right? We know from, if we have data in a very simple, nicely structured way, we know how to make certain operations very, very efficient. Okay? But it supposes they're in a nice format. And I'll call this an abstract representation of the data. It'll be something like a list, a set, a point set in high dimensions, a matrix. We'll talk about how to get into these structures. And there's a lot of work in converting into these representations so you can run an algorithm. Right? Your data is not going to be presented to you typically in these nice representations. You have to work to create this. Right? And this is we'll talk about these challenges. And then once we have this representation, then we can run these efficient algorithms. We can choose an algorithm to make this efficient, to solve some problem. And then there are issues in scalability, error, and modeling. So the modeling is, which algorithm do I run? Right? The choice of the algorithm is going to, affect, what the output is, right? And they're not going to be, and, you may have touched on some of this in your algorithms class if you took it last semester here, the advanced algorithms class. But, the algorithms don't always return a precise answer. The goal is not always just to sort a list, there's one answer. It's to return some quantity and you can return it approximately. Right? Often if you allow some error in the answer, you can do things much faster. And we'll talk a lot about these sorts of trade-offs. And this scalability, the error, and the modeling all interact together in some very messy way that we'll need to think about. Right? And so you need this bag of choices of techniques to know what are your options to trade off, and then you need to make some decision. Okay, so, a lot of what I talked about here could have been covered in other classes, right? There's this machine learning class, which, how many of you took the machine learning class last semester? Or in the past? This is maybe like a third of you. Okay, so that's good. You don't need to take machine learning before this. I'd recommend taking this and the machine learning class. We've tried to keep them fairly without too much overlap. The machine learning class is focusing largely on one very important problem, is given data with some label, say true or false, yes or no, the customer bought something, they didn't buy something, a sports team, they won the game or they didn't win the game, and then trying to make prediction on new without seeing that label. Right? This is one really important, and we'll try and focus on many other questions instead of this one. So this is trying to be a more catch-all class. There's a huge set of techniques just for solving this one classification problem that we will mainly not talk about in here. And there's a bit more continuous optimization. This class will be a bit more discrete. Which may be more familiar to computer scientists, maybe less familiar to statisticians. Okay, there's this artificial intelligence class, another great class is going on this semester as well. And this is kind of closer to machine learning, but it's about interacting more with the world and the data. There's this kind of, you observe, you learn, and then you act, and you gather more data based on what you've learned. And it's more about this feedback that's going on. There are a lot of techniques there that are very relevant to what is going on in data analysis. We're mainly not going to cover these sets of techniques in here, where you're more interacting with how you're collecting the data. This is, in our department, this is usually taught by faculty who work who do a lot of work in robotics, and so that may kind of bias sort of examples that they do there. But there's a lot of ways you interact. If you are building a website, customers are interacting with it, and that's how you get new data. And so these are very important in many sorts of data analysis, not just in robotics. And then there are all these advanced classes that we offer. I've listed 4 here: probabilistic learning, structured prediction, natural language processing, clustering. These are all great classes. And this class will overlap with all of these, but probably around 10% or less. Okay, so there's lots of other great stuff going on. If you have a chance, take these classes too. But if you've taken these, you won't have, I don't think you'll have too much overlap with this class. Okay, so kind of another way of viewing this, and this will be this pull between modeling something and computing with it, so it's making it so it's efficient, how you can work with it, right? So in algorithms class, we'll talk about the efficiency. That's the goal of the algorithms class. If you work in statistics, you're almost entirely working in the modeling, right? You want to take some data in some format and figure out what is the right way to think about an underlying model which, say, generated this data, or does the data fit some sort of pattern? But very often, they will not think at all about how do you compute that, or how do I scale this up to large data sets. And so a lot of statistical techniques were developed before we were starting to think about computers, right? 100 years ago, when people started to think about computers, 50 years ago, right? So where the data mining class will sit somewhere in between, right? We're going to think about techniques that are useful for modeling the data, but we're not going to do anything that you can't compute. You can't do it efficiently, right? And there's going to be trade-offs. There's going to be some things that are better at modeling but are much slower, and some things that are much faster with worse modeling. And you need to keep this in mind whenever you're processing data, especially large data. So we'll talk about some things that are designed very especially for very, very large data sets. We'll have like one lecture on doing stuff on MapReduce and similar families of distributed systems. We'll talk about streaming algorithms some, where you can only read the data once, it's coming in so fast. Those are very much on the efficiency side. Other ones will talk much more about the modeling. So we'll talk across the spectrum. Okay, so now I still really haven't told you what we described here, and I also want to point out that some of you may have even taken a data mining class at some other university, maybe even at the same university maybe even here, but in the business school, for instance. So I think there are lots of great stuff to cover here. Every class is going to be a little bit different. When I started teaching the class this way about 5 years ago, most classes were not taught this way. Now a lot of the top universities, this is how they teach the data mining class. Right? So the Stanford and us around 5 years ago were teaching it this way, and now a lot of places are teaching it some flavor like how we're doing it. So, it's going to focus a lot on the large-scale techniques, right? So we're much more on things on the efficiency side than the standard data mining textbooks from 5 or 10 years ago. Will be a lot of broad coverage, so I'll try and give you kind of really the key things that you should know if you take a data mining class. So we'll spend like a third of a lecture on like these association rules, just because you should know what they are. But we'll be talking a lot more about new developments in different areas. So a lot of maybe 20% of the content is maybe 5 years old or even less. Okay, so these are very new developments in here. And I'll try and, my way of presenting stuff is I'll present it from a very formal mathematical viewpoint. I'll try and describe things using mathematical notation, and I'll try and bring you up to speed. So I know some of the notation I'll use you may not have seen before, so I'll explain it at the beginning, but you'll be used to it by the end of class. The reason I do this is because my goal with you at the end of class is you can pick up a recent paper in data mining and read that paper and evaluate, is this, I kind of know I've seen a similar idea used before, I can read this paper, understand the new idea, and kind of get a sense of whether this makes sense or not. If you're going to be working in this field, in data science afterwards, things are going to keep developing. There are going to be new ideas after you leave this classroom. And I won't be able to teach things that haven't been invented yet, so you will have to pick up the paper or read a blog post about it or something and understand it. And it's going to be probably written in the sort of mathematical notation, how they'll explain it, that I will use in class. Okay, but what we'll try and do is I'll present things with this notation, but in the homeworks you will often be more implementing and working with the techniques. Okay, and then in the projects you get to go deep into some particular topic. Okay, and if you haven't seen it before, and some people haven't taken the advanced algorithms class, there'll be some probabilistic algorithms, or these randomized algorithms, where we need to use randomization, and we have probabilistic guarantees on how well things do. And I will discuss these sorts of algorithms. They may be new ideas to some of you, but we'll try and build them up a little bit slowly. So that'll be some of the new kind of ideas brought in. Okay, there will be no specific software tools or programming language we'll be using. We're not going to be using like some data mining library and just going through the tools. I expect if you're in this class, you should be able to pick up a library and sort things out. It should be not too hard to figure out what those options are once we've discussed them in class. What I think is more important is understanding what those different techniques are doing. And so that's what we'll be focusing on. I may ask you to implement something. It shouldn't be too hard. The focus of the class is not to make you code up a lot of stuff, but to see how things work through coding. Okay, and there's not a specific programming language. Some stuff will be designed a little bit better for MATLAB, because that's the easiest way to do it in. Some are going to, MATLAB will not work so well. You want to use Python, Java, C++, something where you can use data structures. Otherwise, it's going to be not efficient enough. Okay, and the maths we'll use in this class, this is so this is the British form of math with an S, but that's because there are multiple areas of mathematics. I didn't write all mathematics on here, but so the important ones are linear algebra. You should have some background in linear algebra. I will try and build up everything from first principles, but some things will go quickly if you're not used to working with matrices before. We'll talk about probability. Well, these probabilistic algorithms, if you're not used to probabilistic concepts, these are going to be harder to grasp what's going on. There's not a lot of specific from the probability class, right? If you took a probability class, there's not so much specific from there other than like expectation and random variables. But the kind of conceptually, it may be hard if you're not used to thinking that way. And then we'll end up doing a lot of high-dimensional geometry. Now, I don't expect most, if any of you, to have much background in here, so this I will not expect that in how I deliver the material. But there'll be a lot of cool, very cool high-dimensional geometry, which is sort of stuff I like in my own research. That comes up a lot in these topics. Okay. All right, so what is the basic outline of class? Okay, so now we're kind of getting down to what are we actually going to cover. Okay, so I kind of try to break the structure up into a few different, into some different topics here, and I'll go through each of these in like about a slide on each of these. But we'll kind of give some background on statistics and just the principles, the way to think about it. We'll talk about data and distances, and then finding structure in data. This is what maybe is most commonly thought of as in a data mining course. This is like the core of what people think of. You're mining for structure in data, and then controlling noise and uncertainty. And this is just the, I don't know, it doesn't really fit link analysis, but I'll talk a little bit more about this as we go. This is more of dealing with large graphs and issues with there. So let's go a little bit more detail in each of these. So statistical principles, what I want to go over is this, there's this really powerful tool that comes up a lot, which is this using these, these hash functions to work with large amounts of data. Okay, and so the idea is you have some data set. You could be writing a program to sit on like a router, and you have these IP addresses coming through, right? And so there are billions of different possible IP addresses. You don't want to store a list of all IP addresses. You want to keep track of them or some statistics about them. So what you do is you map each IP address into a random cell in a hash tree. Okay? And then you can keep track of, do I see that again? Do I see that one multiple times? Or, there's certain questions you can ask. There's again, words in a dictionary. There could be new words that are being invented all the time, so you don't want to predefine all the words. You just map them to a random cell. You just want to keep some general statistics about them. You can keep some information about what's stored there as well if you want to. There are various things you can do, but this comes up all over the place where you have these objects and you want to map them to some sort of representative index, right? And so you want to do this randomly, and there are kind of these important statistical effects that kind of happen. When do you first get some collision between two objects? How many different items can you put in here before you expect to see a collision? Okay? So how many until you expect that two end up in the same bin? Right? Then you say, how many do I expect until each one of these cells has at least one item in them, that I've filled them? Right? So you want to get some sort of coverage of something. I want to get an example of every possible user for a website I'll see. I map them to different categories. I want to see every single user. At what point does this happen? Right? And this happens once you get even more data, right? And then what happens when all the data is roughly uniform, right? This is the average of all the cells. When are all the cells about the same? Okay, this last one is I'll shoehorn into this same hashing setting, but this is a phenomena of what's called, this is a phenomena so-called concentration of measure, right? When you've seen enough small events that on average they all look like you expect them to look. Okay, and so this concentration of measure, where you kind of aggregate many, many small independent things into kind of get a view of a much more bigger, complicated object, is a really important scenario. It's a really important kind of tool that comes up. And so I'll give you some basic intuition and tools about how to think about these things. Okay. Then another part of this that we'll start getting into actual data is kind of these various ideas of converting kind of some sort of messier data, not like all the way down to you have to like. I'm not going to talk at the level of scraping something from a website, but assume the website has been scraped, something like that. How to convert it into an abstract representation. So how to think about text, a large text file, and convert this into a point set, or just convert it into a set, right? That still captures enough about what is going on, right? Or if you have a graph like a social network, or the graph linking web pages together, how to convert this into a matrix, and then to work with the matrix, you should really think about this as a point setting. So we'll need to convert a matrix into a point set. Okay, and so then from a table with a bunch of different quantities in that, how to again convert this into a point set, and these are objects that are a lot easier to work with and think about and to develop algorithms for. So we'll talk a lot of things through various parts of the class, these conversions into these abstract representations, where we can then apply what we know from, say, an algorithms class, or specific things we'll talk about in here. Okay, and then what are some of the tools that we'll think about? Well, we'll think of, say, having a point set, or some other sort of set of objects that we have distances between them. And we want to talk about similarity between these objects, right? There are a couple of important questions. Given a new data point, Q, so this one is new, I want to say, is this one already in the data set? Or if not, what is the closest other object? Maybe this black one is the closest one already in the data set. This maybe gives me, I can predict something about Q by finding the closest one, for instance. Or I want to find the set of closest ones, or I somehow want to map it onto closest one in the data set. This is an operation that comes up inside of many other techniques that we'll use and talk about, and is interesting in its own right. So just this similarity question. How do you quickly do this? Right? If your data is one-dimensional, right? If your data is just has just kind of, everyone is sorted by their age. Finding someone with the closest age to yours is simple, like searching in a sorted binary list, in a sorted list, right? But when you have multiple dimensions, this becomes a lot trickier. Okay, so we'll spend couple lectures on this. So another one is clustering. You have a large data set, and you want to break it into groups, where the groups are themselves similar, and the groups are different from all the other groups, right? So say this is your data set, I've broken it, the black ones are the data set, I've broken it into, let's use the pen here, into like these three parts here, and maybe I have a representative point, which is this blue one, and we'll talk about why the representative point might be useful. So this is the standard, example of this is k-means clustering, which some of you may have heard of. We'll also talk about some other variants. The same ones we'll mainly talk about in this class, but there's a variety of other things. There's a whole class on this topic that's being offered here. All right, so we'll talk about clustering algorithms. Another topic we'll talk about is going to be regression. So many people have heard of linear regression. Okay, great. So I'll basically more or less assume you'll have known linear regression. I'll go over it, I'll redefine it briefly, but then we'll mainly be talking about extensions of this, right? More advanced ways of dealing with regression. So regression is actually a prediction problem where you have a bunch of, say, multivariate data and this one labeled data point, a valued labeled data point. You want to predict this value based on the multi-dimensions. But I'll talk about these sets of problems more generally by saying you have high-dimensional data and you want to find some linear representation here of this data. Right? So I'm going to map all these points onto this linear representation. And this is kind of regressing these points onto this linear representation. Okay, so the traditional ordinary least squares way of doing linear regression is a specific way where you map them in the axis that you're trying to understand. But there are other ones based on PCA where you're mapping things to the closest point that are kind of structurally different in how they operate. And there are other ways about you have very high dimensional data, you want to project it to a low dimensional space. We'll talk about these techniques as well. This may be called like dimensionality reduction. Yeah, so let's see. So we'll very quickly overview L2 regression and PCA. We'll talk about multidimensional scaling, which is fitting in this low-dimensional subspace and some variants of this, including some, if you took the math for data class with me last semester, we'll talk about a very different approach based on random projections that is much faster for very high-dimensional data. Talk about these matrix sketching. So the core operation in many of these approaches is actually some polynomial operation, right? It's like n squared or n cubed. So if you have huge data sets, that's not feasible. The people run these on millions of data sets, and a million squared or cubed is not feasible. So you can compress, sketch the data first, and then run it on the sketched versions. We'll talk about these techniques here. Most of this machinery has been developed in the last decade, right? Some very new ideas here. We'll talk about these L1 regression, which are ways that are going to be more robust to outliers. And so we'll talk, there are a variety of ways to do this. We'll talk about a couple of algorithms. And I'll mention like this area called compressed sensing, which is how you can recover recover properties from data that you wouldn't think would be possible, but they work because you assume that there's structure. If you assume there's structure in your data, then you can actually do better in kind of finding that structure. So there's some advanced things beyond typical L2 regression and PCA we'll talk about. Will be most of this topic. Okay. We'll talk about throughout the semester, but we'll have a couple of lectures on exactly how to deal with noise in the data, with outliers, when your data does not exactly fit the model you think, how to deal with these questions. And this will include, I'll talk about this cool recent development in privacy called differential privacy. And kind of from a very high-level view, it says, I want to release data so I can let other people work with it without revealing information about the individual data points themselves. For instance, these could be customers, right? So you don't want your people to know exactly what one of your customers was doing, right? So the idea is you kind of add noise into the data in the right way, and so you can still capture the broad structure that we learn how to do in this class, but you don't reveal stuff about individual customers. Okay, so there's kind of some cool stuff we'll talk about here as well as some like ethical issues. I'll try and mention them throughout class, but we'll spend some time just on this as well. I think it's important to kind of get a sense of this before you go off into start doing stuff with data without worrying about the consequences. Okay, and then we'll talk about the last section in the semester will be like on this link analysis, dealing with large graphs. Okay, and this will be fairly different than the rest of class and how we think about the original data. It's a little bit, it's got some structure to it that's harder to convert to a point set, which we'll be able to do in a lot of other areas. So we'll talk about like how do Markov chains work. And these are kind of key in understanding the large level structure of graphs. So we'll talk about Markov chains, and then PageRank is kind of essentially is a Markov chain. So who's heard of PageRank? Yeah. So if you don't know, PageRank is like the so who could describe to me how PageRank works already? So people have heard of it, but don't really. Okay, great. Good. So that's the perfect way. You know the buzzword and you don't know what it is, so you're thinking about it. Good. I've got. So PageRank is using Markov chain analysis on large graphs to find out which nodes are important. and this is the basis of what made Google's search engine better than everyone else's, and led to them being able to become this, enormous company, right? There's this really cool insight. And we'll talk about how that works. It's a little bit more than just a markup chain. You need to do some other stuff on top of it. We'll talk about how this interacts with MapReduce and these other kind of large-scale tools, about how to deal with massive data that doesn't fit on one computer. This also came out of Google, and one of the core reasons they invented it was to run pagering on the web graph. And then we'll talk about finding communities in these graphs. So if this graph here, if this is if this is Bob and this is Sue, right, and they're friends with each other, then there's an edge between them, right? This is like then this can be a, then this is how you would, one way of modeling like a social network. Now there's lots that can go into what is an edge and how strong it is, but like those are kind of a lot of modeling details. The core is to say, how connected are parts of the graph, right? If this part is much differently connected from this part, there's like these tighter communities in the graph. How do these communities form? What structure do they have? How to think about these sorts of problems. Okay. So this is within the graph, and this is related to the clustering problem, but there's some different ways of thinking about this as well. You don't necessarily need to cluster in order to find these communities. Okay. Oh yeah, and so throughout the class, won't be kind of an individual section, but we'll talk about these summaries of large data. This is kind of another thing that deals with the scale. They'll deal with this streaming model where you're kind of reading through this data like you're on a router. This is like your algorithm, which sits on a CPU or sits on a router, and as data is coming through, you can read it once and then it flies off into the ether. You can't store everything. So how do you keep a small space representation of the data? And there are a lot of kind of really cool things you can do in this space, and so we'll talk about a few of these. And these will interact with a lot of the other problems we'll talk about. Right? When you want to scale them up, you often want to, if you can do them within a streaming model, it means you only need to read your data once. It means your algorithm must essentially be linear, plus some small amount of processing in here. Right? So if you have a billion items in your data set, and you need to keep a summary of the size 1,000, you can be polynomial algorithm in the size 1,000, as long as you only read each of the billion things once. Right? So this is a kind of a really important tool to deal with really large scale data. So we'll sprinkle some of these summaries and streaming algorithms throughout the semester as well. Okay, so so just kind of remind you the themes again. Now that you've seen the topics, I want you to get an intuition for how to do data analytics, how to think through starting from some messy data and then to getting to choosing an efficient algorithm to run on it and interpreting that output. All right, that's kind of one of the goals I want you to get out of the class. Right now, I can't cover all of the techniques in this area. There's this huge list of techniques. Some of these you need to go to more advanced classes to learn these things. But I want to try and survey these and give you, so you can learn this intuition, and hopefully you can pick up some new techniques on your own once you kind of see how to think about these and put them into the right pipeline. Right? And a core part of this I really want you to get out is to kind of thinking about from messy data into these abstract data types. Right? You can think of, you've got, you have messy data, convert it into the abstract data type, right? Once you have it in here, then you can run various algorithms on top. So we'll talk about these various algorithms you can run on these abstract data types, and you're going to have to still, once you even do this, you still have to choose which algorithm to run and how to interpret this. Right? But you should think about first converting it into here and then choosing. And this conversion process, this always induces error, okay? Now there are two types of error. One is the error, I've run an algorithm, maybe it's an approximate algorithm, it induces error there. There's another error here, which is the modeling error. I've chosen to model the data as a point set, as a matrix, as a graph. That's not exactly what I saw or what's really going on. There's some modeling error here, and so you have a choice of how to do this as well. And so most people don't think about this as really a core challenge. They may just say, well, I'll do it, but they won't think about the consequences of this conversion. Right, yeah, and so then there's this whole thing about the spectrum of balancing the modeling versus efficiency. These choices that you make, you can run an algorithm that's a great model, and it will take 2 years to complete running it. So it's not useful, right? This trade-off between the efficiency and the modeling, right? So we'll see lots of different things, and we'll think about these trade-offs. Okay, so roughly each of the topics we're going to have spend about 2 to 3 weeks on that I covered and had a slide on. And so the goal is to kind of really overview the really classic techniques so you know those, and those will be more of the focus of the homework. Those will always be in the homework, but we'll also want to go over some special advanced topics that I think this is a new thing that's going to become more important, or it's new and already is really important. And maybe it's more specialized, but I think it's really cool. I think you'd like to see it. So we're going to kind of balance both of these aspects. And we'll focus on this modeling efficiency trade-off. Yeah, so, and the homeworks will mainly be, we'll give you fairly clean data to work with. The goal is for you to kind of see how data works once you get it into the right format. And to kind of play with the knobs of an algorithm or implement it a little bit differently and seeing the effect of doing it. And so the homeworks will be about 45% of the grade, or 45%. Well, the 2 tests I mentioned, those are 10%, and the course project is 45%. Okay, so a mention on the grading here. So, so I mentioned if you get kind of 90 and above, it's an A or A minus. 80 and above, it's at least a B minus. So how proposal, really get 100% of those if you follow the instructions. Every year, a few people forget to follow the instructions, right? But and then on the final part, I will give an average product. That's the 50% of that grade is on the final report, right? The average project in the class, I think I'll give 45 out of 50 points. Okay? So to get 50 points, you have to, so 100% of the project, you have to go above and beyond average. Just because some people always go above and beyond, and I want to make sure those people are given more points for that. If you do an average project, you satisfy the requirements, you're still getting like 95%. Okay? The homeworks, some people can fly through these, for some people they're challenging. We have a very diverse class in here. Maybe a third of you are not in the CS program either as an undergrad or a graduate student. I think there are about 40 undergrads, and then in the 5140 class, and then about 100 and 110 people in the 6140, which includes people who are not in the CS program as well. Right, so there's a very big range here, and I think everyone should be able to do well in the homeworks, but for some of you this will take more time. The tests, I think there'll be some division on the grades in the tests, but they're 10% of the grade. Okay, so study, do well. I expect to be able to see who understands stuff and who doesn't on the tests. But it's not, if you bomb the test, you're not going to, it's not going to destroy your grade in the class. Too bad. Right? So hopefully everyone does well. If everyone does well, I'm happy to give everyone a good grade. Right? I don't feel like some fraction of the class needs to fail. Okay? So just to kind of keep that in mind. The people who tend to do well in the class are the people who come to class and pay attention. It's usually, or are watching live streaming. You know, if you watch every lecture, you pay attention, that's highly correlated with doing well in the class. You know, not every semester, not everyone does that. You know, sometimes, you know, but you should try and go to the lectures, it'll help. Yeah, so homework, so you manage your Canvas. Always turn everything into there, mainly as a PDF. So any programming language you can use. I'll try to add some bonus questions everywhere. These will be worth like 1 or 2 extra points. So if other stuff is simple for you, hopefully these are a bit more challenging. You can make back a few points this way. So all homework turn-in will be through Canvas. The grades will be assigned there. Announcements through class. Did everyone get the announcement I sent out? Or they can find it, okay? If you didn't, I sent out an announcement and I put one discussion in there. Use the discussion. Don't post potential solutions on the discussion board, okay? And so, you know, this is a big class. I can't deal with email from all of you efficiently. It's much better to post it on Canvas. You know, so I'll ask you to please do that. There are some situations where I realize you email me, that's fine, but if you think it might be appropriate for the discussion board, it probably is. Someone else will probably be will find it useful. So please post there. I will reply, and the TAs will be replying as quickly as we can, probably more quickly than email.